During lunch at the court, Yari, who is 60 kg, is running east at 5 meters per second, trying to control the ball. At the same time, Gediel, who is 70 kg, is jogging at 4 meters per second at an angle of 30 degrees north of west while heading towards the bleachers. They collide and bounce off of each other, then move in different directions. Since they do not stick together and no energy is lost, the collision is elastic. These are the givens and required. So our givens are mass 1, which is Yari, who is 60 kg, mass 2, which is Yediel, who is 70 kg, velocity initial 1, which is 5 meters per second east. And then initial velocity 2, which is 4 meters per second at 30 degrees north of west. This is my required. So we need to find the final velocity of Yari, final velocity of Yediel, and then the final speed and direction of Yari, and then the final speed and direction of Yediel. So this would be our diagram. We have Yari right here, who is 60 kg, and then we have Yediel, who is here, and is 70 kg. Yediel and Yari both collide, and Yari is going at 5 meters per second, and Yediel is going at 4 meters per second. And then the angle would be 30 degrees. So these are my formulas. Our first formula is P equal to mv. This is our second formula. X plus mass 2 times v2 initial y equals m1 v1 fx plus mass 2 times velocity 2 f of x. And now we have the same formula, but it would be for y. So we have m1 times v1 initial y instead of x plus m2 is v2 I initial y equals mass 1 velocity 1 f of y plus mass 2 times v2 f y. And our next formula is kinetic energy equal to 1 over 2 mass times velocity squared. And this is our second formula. Mass 1, 2, v2 squared initial equals 1/2 v squared plus 1/2 and 2v2 of f. I'm pretty sure I'm missing an f right here. Okay. Next formula is Vx equals V cos the angle. There's supposed to be a little line there. I'm gonna continue my formulas. I just have two more. So V equals square root of V squared x plus Vy squared. Our next formula is the angle, tan power -1 times Vy over Vx. So the type of collision. In our scenario, the type of collision is an elastic collision. Let me just write that down. Collision. And so there's three different reasons why this is an elastic collision. Our first reason is because kinetic energy is conserved. Our second reason is the students, or Yari and Gedyel, bounce apart instead of sticking together. And our third and final reason is momentum is conserved in both x and y directions. Okay, so there are four different types of collisions. The scenario I used has an elastic collision, which is when the object bounces off of each other. But there are three different types, or no, four in total, but there are three others. So there's an elastic collision. So an elastic collision is when an object hits and loses some kinetic energy. So for example, heat, sound, yeah. So momentum is conserved and kinetic energy is not conserved. Our second type of collision is perfectly inelastic collision. So perfectly inelastic collision is when objects stick together after they collide. Momentum is conserved and kinetic energy is not conserved. And the fourth and final type of collision is explosive collision, which is when an explosion happens. So explosive collision is when one object breaks into pieces and pushes apart. Momentum is conserved and kinetic energy increases, and this comes from stored energy. Okay, so now we're moving on to our substitution, which is a very long process. So first we must resolve Brian's initial velocity into components. So we'll do E2ix. Initial x equals -4.0 cos times 30 degrees. We're going to do E2ix equals 4.0 times 0.86 v2ix equals negative 3.46. Nice. Okay. Now we have to do the y. v2iy instead of x now. It's 4.0 sin. We're using sin because we're talking about the y direction. v2iy equals 4.0, 0.5, and v2iy equals 2.0 meters per second. So okay. So now we are on step 2, which is substitute into momentum conservation. This is the formula we will be using. It is a long one. v2x equals m1 v1 half of x plus m2 v2 equals half of x. So that is our formula. Now let's plug in our values to our formula. 60, 5.0 plus 70 is negative 3.46 equals 60 v1 f of x. And then over here, we'll come here because we ran out of space. It's going to be plus 70 v2 f of x. Then we have 300 minus 242.2 equals 60 v1 f of x plus 70 v2 f of x. Now we do 57.8 equals 60 v1 f of x plus 70 v2 f of x. Our final answer is going to be just that. 57.8 equals 60 v1 f of x plus 70 v2 f of x. Let's erase this. Okay. So our third step is to substitute into momentum conservation, but except this is the y direction. What we just did was the x direction, and now we're doing the y direction. So it's the same formula, except we were just talking about y. 2 v2 m1 equals m1 v1 plus m2 v2 f of y. Is that? Now we'll substitute in our values. It was 60, 0 plus 70 minus 2.0 equals 60 plus v1 f of y plus 70 v2 f of y. 0 plus 140 equals 60 v1 f of y. Oops, there would not be an I there. So it's v1 f of y plus 70 velocity squared f of y. And because 140 plus 0 is equal to 140, Down here, we're going to write 140 equals 60 v1 f of y plus 70 v2 f of y. Let's see. So step 4 is to substitute into kinetic energy. This will be our formula. It is also a very long formula. Okay, so that is our formula. Can you see that? Yeah, you can. All right, so now we have to substitute our initial values. It's 1/2, 60, 5.0 squared plus 1/2, 70 squared. Times 4.0 squared equals 1/2 times 60 v squared 1/2 plus 1/2 is 70 times velocity squared 2f. This just goes right here, but we ran out of space. And from there, we solve, we multiply, and we get 750 plus 560 equals 30 v, then velocity 1 to power 2 plus to 35, velocity 2 squared of f. And then we get 1,310 is equal to 30 velocity 1 squared f plus 35 velocity 2 squared of f. And now we have to expand the final velocity into components. So let's see this. Okay. We're expanding our final velocities into components, so it's v velocity 1 squared f plus velocity 1 squared f of x plus velocity 1 squared f of y. And then, no, it's the same, but for velocity 2, it's velocity 2 squared of f equals velocity 2 squared f of x plus v, or velocity, the second velocity squared f of, so now we have to use a formula here for substitution. N equals 1/2 m squared times v1 f of x squared plus 1/2 and times 2 times v2 f squared. And now we can do our substitution. So now we substitute our numbers. 1,310 equals 30 times velocity 1 squared f of x plus velocity 1 squared f of y plus 35 times velocity, the second velocity squared f of x plus velocity, the second velocity squared f of y. And now, after we substituted, we can now distribute. So now we get 1,310 equals 30 velocity 1 squared f of x plus 30 velocity 1 squared f of y plus 35 velocity 2 squared f of x, and then plus 35 velocity 2 squared f of y. Let's see this next steps. Now we have to solve momentum equations. Pretty sure x and y, so So now we have to solve momentum equations. So the x direction 5.78 equals 6v velocity 1 f of x plus 7v for velocity 2 f of x. Now the y direction would be 14 equals 6 times velocity, the first velocity f of y, plus 7 times the second velocity f of y. So here we have, now we move on to Guedjel's components. So we have E, V2 f of x equals 5.78 minus 6 velocity 1 f of x by 7, and then we have v2 instead of f of x, we have f of y, this equals 14 minus 6v divided by 7. Okay, so after using conservation of momentum, I apply the elastic collision velocity equation in the x direction and then repeat the same process in the y direction to find the final velocity components. So right now, I'll be solving for the x direction. Put that right up here. Okay, so the formula I need to use is mcx vcx plus mcx vex equals m1 v1 x plus mc vcf x. Okay. Now we have to do k1 plus v1 f of x equals v2 plus v2 f of x. So we do s plus v12 equals -3 point 16 plus VET, and then 1 f of x equals negative 8.16 plus VET. So now we have to substitute in our values. Let's do 60 times 5 plus 70 times negative 3.46 equals 60 times negative 8.41, sorry, negative 8.46 plus VET. I'm going to continue it down here because I ran out of space. Plus 70 VEF of x. Now after substituting our numbers in, we have to distribute. So it's 300 plus negative 242.2 equals negative 507.6 plus 230, second velocity F. Then we get 807.6 minus 242.2 equals 130, second velocity F of x. Now we do this here, we get 565.4 equals 130 VE F of x. And now we divide. Do we divide? Yeah, we do divide. We divide 130. Okay, so that goes. Okay, so we get 35 equals VEF of x. We get velocity 1, f of x equals negative 8.46 plus 4.34, and that gives us 4.12 meters per second, and this is just for our x direction. Yes. Okay, so now we should be doing, now we are doing the same method, but instead of x, we're doing y. So let's do our formula. Iy plus velocity 1 f of y equals v2 iy plus v2 f of y. So now we have to substitute our initial values. Remember, now we do viy equals 0, v2iy equals 2.0. Now we substitute. And we do 0 plus velocity 1 f of y equals 2.0 plus v2f of y. Oh yeah, okay, so now it's v1 f of y equals 2.0 plus v squared f of y. Now I have to plug into y momentum equation. Erase this for fresh start. Okay, so it was 60 times 0 plus 70, that's a 7, times 2.0. This equals 60 v1 f of y plus 70 v2 f of y. And then now this simplified or distributed, it's 140 equals 60 v1 f of y plus 70 v2 f of y. Now we substitute again. We do v1 f of y equals 2.0 plus v2 fy. Check something quick in my notebook. Yeah, wait, yeah. Okay, after that we do 140 equals 60. 2.0 plus v2 f of y. It's a 4. I'm going to change that to a v. And then v1 f of y. Oops. Let's see, where did I mess up? Where did I mess up? Okay, let's see what I did. 140 again equals 120, which is just this. We just distributed this 6 into these variables. I actually forgot something up here. It's plus 70 squared f of y. Not bad. So 140 equals 120 plus 60 v squared f of y plus 70 v2 f of y. We get 140 equals 120 plus 130 v squared f of y. I'm just gonna erase this for some more space. Okay. Okay, so now we solve. 20 equals 130 b2 f of y. Is that right? Yes, that's right. Take v2 f of y equals 0.154 meters per second. And now we have to solve for velocity 1 f of y. So we do v1 f of y equals 2.0 plus 0.154. And velocity 1 f of y is now equal to 2.15 meters per second. And so our final y components would be .15 and 0.154. I'll write it out. F of y equals 2.15 ms meters per second. Oops. And then velocity 2 f of y is going to be equal to 0.154 meters per second. Nice. Okay. Okay, so these are my final components. My final components would be Yari, and then Yehiel. So it's V1 f of x equals 4.12 meters per second, and then V1 f of y equals 2.15 meters per second. And then V2 f of, oh no, sorry. This would be for Yehiel. Would it be? Yeah, it would be. So our first one is going to be for Yehiel velocity 2. It's 4.34 meters per second. And then velocity 2 f of y is going to be 0.154 meters per second. Okay. And now, I'm pretty sure we have to calculate the magnitudes. Yes, we do. Now we're calculating our magnitudes. So velocity, this is our formula for our magnitudes. V equals Vx squared plus Vy squared. So this is Yari's final speed. Even though that's a sped, we'll fix that. So we'll do V1 f equals square root of 4.12. Oops, it would not be a 12, it would be a 1 squared plus 2.15. And then that turns into v1f equals 16.97 plus 4.62. And v1f equals 21.59. And then we get v1 equals f. And then that gives us 4.65. So now we can erase this. And instead of Yari's final speed, we're going to do Yel's final speed. So Yel's final speed would be velocity, second velocity f equals 4.33 squared plus 0.154 squared. This is going to give us 18.84 plus 0.024. And we get 18.86, and then we're met with our final answer of 4.33 meters per second. Okay, so now I'll give you my, hands hurting. I will give you my final directions for Yari and Didier. This is the formula. Angle tan -1 Vy over Vx. Okay, so for Yari, it's going to be it's going to be 2.15 over 4.12. That is not clear enough. 4.12. And then it's 27.6 north of east. Okay. Now the idea is -10, -1, 0.154, and then 4.33. Looks like a 6. That to a 4. And then we get 2.0. So these will be our final directions. This one will be for Didier, and then this one will be for Yari. Now, our equation is done, but we need to verify it. So we will use this formula to verify our equation. F. It's your formula. Now with the numbers we were given in the scenario and with our final direction, we can start substituting. 65 and 7 plus 70 times 4 squared equals 60 times 4.64 squared. And right down here, because I'm running out of space, plus 70 times 4.34 squared. And then that gives us to 620 equals 2615.80. So even though these two aren't exactly the same number, it's still close enough. for it to be verified, for it to be marked as correct. This is my paragraph answer, our final answer. So using momentum and elastic collision equations, I found that Yari is equal to 4.65 meters per second at 27.6 degrees north of east, and Yedyel is 5.33 meters per second at 2 degrees north of east after they hit each other, or after they collide.